Hey, we are going to look at alternating series in this lesson and how to determine if an alternating series converges or diverges. And I am not going to cover error approximation in this lesson. So if you are looking for that, you need to go find another video. And if you want to print the sheet that I give to my students to follow along for guided notes, you can go to this bit.ly link right here. And let's go on and talk about alternating series. And an alternating series is given that name because the terms of an alternating series swap between positive and negative and positive and negative and positive and negative through the duration of the series. And your alternating series can be written in that form. And the key that makes it alternating is this -1 to the n power. That right there is the source of the alternating aspect. Some alternating series are kind of disguised. You may not see the -1 to the n, and we will look at an example like that in a little bit. But that is generally what you will see. Sometimes it's raised like to the n plus 1 instead of -1 to the n, but that will create the alternating aspect. And the a sub n in both of those examples is a positive sequence. So let's go on. One good thing that can help you with alternating series that may allow you to bypass the alternating series convergence test is that if the absolute value of your series converges, so if you take all of your terms and make them all positive, if that one converges, then so will the original series that alternates. And the reason for that would be through direct comparison. If you make all the terms positive, then you are making the series larger than the original. And if it still converges, that means the original would also converge. So if you can, try considering the absolute value of your series. And if that converges, then you don't need to worry about the alternating series test. And if the absolute value diverges, that tells us nothing about the convergence or the divergence of the original series. I thought I deleted that. There. And so this fact only works if the absolute value of your series converges. And to show you an example of how that would work, we do have an alternating series right here. We have -1 to the n over n squared. However, if you applied the absolute value to that, it would turn into the series from 1 to infinity. Well, the absolute value of -1 to the n would be +1. It gets rid of that alternating aspect. And we have +1 over n squared, and that is a p series with p equal to 2. That is greater than 1, therefore this converges, which means, a bigger therefore, my original series, which was -1 to the n over n squared, also converges. And so that's how you can use this little fact about the absolute values. And if it works, it's quicker than going through the alternating series test. But sometimes that is inconclusive, and so there is a test for determining whether an alternating series converges. And you have two conditions you need to meet. First, if you look at only the positive terms of the sequence, if you kind of ignore the alternating aspect of it and you look at the a sub n sequence that is always positive, if that sequence approaches 0, that's the first requirement. And the second requirement is that your terms must be decreasing. And so the n plus first term is always less than the nth term. And sometimes that test for decreasing isn't as clear cut. And so sometimes you may need to show that the derivative f prime of n would be less than 0, with f of n being your sequence. A sub n. But I'll always try the n plus 1 less than a sub n method first before I dive into derivatives to show that the sequence decreases. So let's look at a handful of examples. I have 6 total that I want to look at, and hopefully this doesn't get too long. So first sequence is -1 to the n over n, or series, and I'm going to start by thinking about the absolute value of this. And if you do find the absolute value of this, you get the series from 1 to infinity of, well, the absolute value of -1 to the n is 1 over n. That's harmonic. That's your harmonic series, which diverges, which means that that absolute value approach was inconclusive. Now we need to consider the alternating series test, And if you want to rewrite this so you see the -1 to the n times the other sequence, this could be rewritten as -1 to the n times 1 over n. So in this example, my a sub n is 1 over n. And I need to show that that approaches 0 and that that sequence is decreasing. So the first one I'm going to do is the limit as n goes to infinity of 1 over n does indeed equal 0. So we satisfy that first requirement. So we show that the limit as n goes to infinity of your sequence is 0. And we need to show that this sequence decreases. So is a sub n plus 1 less than a sub n? And, well, if you plug in a sub n plus 1, you have 1 over n plus 1. That is indeed less than 1 over n, same numerator, but the denominator on the left side is larger. That favors a smaller fraction, so that is true. Therefore, my original series, -1 to the n over n, converges by your alternating series test. So there's an example of the alternating series test. And so it turns out the harmonic series diverges, but if it alternates, the alternating harmonic will converge. Let's see, moving on to this one. This one is going to be pretty nice. If you did the absolute value of it, and I always try this first, because if the absolute value approach works, then you can bypass the two-step process for the alternating series test. And if you do the absolute value of this one, we have the series n goes from 0 to infinity, and that would be 1 over n factorial. And this one, just right off the bat, I can tell it's going to converge because n factorial is an incredibly powerful function, extremely powerful. But just to show with maybe a direct comparison, if you expand that out, 1 over 0 factorial is actually 1, so that's 1 over 1, plus 1 over 1 factorial is 1, plus 1 over 2 factorial is 1/2, 1 over 3 factorial is 1/6, 1 over 4 factorial is 1/24, and I'll do one more. 1 over 5 factorial is 1 over 120. And it goes on. I'm going to do a direct comparison to the p-series. N equals, I just noticed something. I'm going to have to start this at 1 because I cannot start 1 over n squared at 0 because I'll be dividing by 0. And so that's going to start over here where n is equal to 1. And 1 over 1 squared is 1. And so we have a kind of a blank, empty spot for that first n equals 0 term. Plus, if I plug in 2, we have 1 over 4. If I plug in 3, we have 1 over 9. If I plug in 4, we have 1 over 16. And at this point, I'm going to plug in 5, we have 1 over 25. At this point, from that term on, I can tell that 1 over n factorial is going to be smaller, significantly smaller than 1 over n squared. And so because of that, as for n's greater than 4, it is true that 1 over n squared is, 1 over n factorial, man, I'm jumbly today, is less than 1 over n squared. And so by direct comparison, since 1 over n factorial is less than a known convergent series, therefore I know that my original series, which was the alternating version of 1 over n factorial, must converge. Right. Now that was a lot of work because this is one you can really look at it and just know right off the bat this is going to converge because that bottom is so incredibly strong. It's very, very bottom heavy. But I did want to show a little bit more detailed explanation for why that one would converge. Let's see, moving on. This one, sine of n over n cubed, and sine n, see this one doesn't truly alternate. This one doesn't truly alternate because if you started plugging in numbers for n, there will be some positives in the numerator, there will be some negatives in the numerator, but it's not going to alternate positive, negative, positive, negative, positive, negative. So it's not exactly an alternating series. However, I do recognize the potential for the numerator to be negative, and so I'm going to take the absolute value of this, and when I do that, if you think about sine n, sine of anything is always going to be less than or equal to 1 or greater than or equal to negative 1, which means that the absolute value of sine n is always between 0 and 1. And so when I took the absolute value of this sequence, well, the denominator n cubed doesn't change, but I shouldn't have written equals, but I do know that that numerator sine is always less than or equal to 1. And so what I'm doing here is I'm using the absolute value to compare this to a sequence or a series 1 over n cubed. 1 over n cubed, that's a p series. P is 3, that is greater than 1. Therefore, I know that 1 over n cubed converges. The series of 1 over n cubed converges. The series I'm interested in, its absolute value is less than a known convergent series. Therefore, the original sequence or series will also converge by direct comparison. So the sequence, or I keep saying sequence, the series sine n over n cubed converges by direct comparison to 1 over n cubed. So we bypassed the alternating series test on that one. Let's see, what about this guy? See, this one alternates, and I see something really nice right off the bat. And this should be one of the first things you always look for with series. This is my a sub n. That's my a sub n. And I can tell right off the bat that if I apply the limit as n goes to infinity of n squared plus 1 over n squared minus 1, degree on top and bottom are equal. If you divide their leading coefficients, you get 1. These terms are not even approaching 0. If the individual terms do not approach 0, that means this series will automatically diverge. That is your nth term test. Therefore, this diverges. And so that's quick. That's nice. If terms do not approach 0, we don't have to worry about any of the other tests. Okay, so let's look at this one. This is a neat one. This is a really neat one. Now I'm going to make another copy of that. I could, on this one, I could try the absolute value trick like I did with sine x earlier. And just like sine of n, I should say n, not x, just like sine, cosine is indeed less than 1. And so this would be less than 1 over the square root of n, which is n to the 1/2. The unfortunate thing here is p is 1/2. That's less than 1, which means this series diverges, the one I'm comparing to. And if you're less than a divergent series, that's inconclusive. So it's worth thinking about the absolute value approach, but sometimes it's inconclusive, and that happens here. But this is a neat function. This is a neat series because it doesn't look like it alternates, but when you start plugging in values of n, if you start to expand this, if I plug in 1 for n, cosine of 1 pi, cosine of pi is negative 1 over the square root of 1. And then my next term, if I plug in 2 for n, cosine of 2 pi is positive 1 over the square root of 2. Cosine of 3 pi, well, that's negative 1 over the square root of 3. Cosine of 4 pi is positive 1 over the square root of 4. And you can see the pattern there. This does not look like an alternating series on the surface. It doesn't have the negative 1 to the n power like we'd look for. But when you write this out, this actually is an alternating series. And I can rewrite this series as negative 1 to the n over the square root of n. As n goes from 1 to infinity. And I'm going to double check that just to make sure it's right. When I'm writing my own series, I will always check to see if the alternating lines up correctly. If I plug in 1 for n, negative 1 to the first power will be negative 1. And I did want a negative first term. So there we have our, we have rewritten this series. And for this one, we've already tried the absolute value thing. We know that the absolute value trick doesn't work. So I'm going to have to go with the alternating series test. And the sequence in this case is 1 over the square root of n. And by the alternating series test, you want to show that the terms approach 0 and that the terms decrease. And so the limit as n goes to infinity of a sub n is going to be the limit as n goes to infinity of 1 over the square root of n, and that will indeed approach to 0, so that checks out. And do the terms decrease? Does the sequence decrease? And it will, if I plug in n plus 1, 1 over the square root of n plus 1, and I compare that to the term just before it, yes, just before it, I have a larger denominator. The n plus first term is indeed less than the nth term. Therefore, this series, which I'm going to bring it back to the original one, this series of cosine of n pi over the square root of n, does indeed converge. Good, as n goes from 1 to infinity. So it didn't look alternating, but it actually did end up being an alternating series. And then the very last one I want to look at is this one, negative 1/5 to the n. I'm going to rewrite this. I'm going to rewrite this guy. That is the same thing as negative 1 to the n times the arctangent of n over 5 to the n. So I'm rewriting negative 1 to the n, negative 1/5 to the n as negative 1 to the n over 5 to the n. And then I'm looking at this, and we're going from 1 to infinity. Let's swap to green there. And this is an interesting one because I can apply the absolute value trick to this one. And when I do that, we have something similar to what we had with sine and cosine earlier. And it is true that the inverse tangent or the arctangent of anything is always trapped between pi over 2 and negative pi over 2. And that is good for you to know because now I can show that this series is actually less than, the absolute value of my series that I'm interested in is less than pi over 2 over 5 to the n. And that's beautiful because pi over 2 over 5 to the n, that's a geometric series with a ratio of 1/5. The absolute value of that ratio is indeed less than 1. Therefore, this converges. I compared it to a convergent series. And the absolute value of the one I was interested in is less than another series that I know converges. Therefore, my original series, negative 1/5 to the n times the arctan of n, will also converge. So there are some examples of the alternating series test, as well as using the absolute value trick, because if the absolute value of your series converges, then so does the original, and you don't have to worry about the two-step alternating series test. And that is all I had, I'm pretty sure, and it is. Thank you very much.